Okay, today it's Library of Functions Day and piecewise defined functions. So what we're going to do here is introduce several functions, somewhat take for granted the graphs produced in the book are the accurate graphs. We're going to get these graphs by plotting points, and I've mentioned probably repeatedly, plotting points is not a good way to graph something unless they're special points and you know why they're special. So the agenda here is really to get the idea of the shapes of the functions in the library. And we'll add to the library of functions a little bit later. We'll add log and exponential functions, for example. So what we're going to consider here is the functions f of x equals the square root of x, f of x equals the cube root of x, the absolute value function, a constant function, f of x equals x, f of x equals x squared, f of x equals x cubed, so some powers of x, f of x equals 1 over x, and finally the greatest integer function. And then we'll look at piecewise defined functions where the pieces are made out of these things here. So, well, I've got it written in the notes. When graphing each function in the library of functions, we plot a few points and trust that the pattern continues for other points. This ain't the way to graph something in the absence of any other knowledge, and maybe it's all you've got. This, in general, it's a bad way of graphing. As I said, you want to plot special points or this idea of there being some pattern that we will assume continues. They have a way in Calculus 1 to confirm that the suspected pattern actually holds. For example, we'll plot f of x equals x squared, which you probably dealt with before. And there's a definite pattern that appears when we plug in some small magnitude numbers. And that pattern does continue, though we don't have a way of dealing with that in Precalculus 1. So take this section with a little grain of salt. I'll tell you this, I've been doing this a long time. It's like 35 years plus. And the approach that Sullivan takes to graphing, it's a bit more sophisticated than a lot of other stuff I've seen out there. So we will accept that the graphs given are what these functions look like. In Calculus 1, you'll be able to go through and have a more theoretical reason for believing that these are accurate graphs. Really, all we got now for the functions we're going to consider largely is plotting points. You want to plot more points, you'll see they follow the pattern that we're guessing based on the few points that are plotted. I will say this on the negative side about Sullivan, the author of the book. For some of these, he don't plot very many points and draws a conclusion that they represent the shape of the graph. First, let's look at the square root function. Plotting a few points, we find the following. Okay, the points they've chosen to plot are square root function 0, square root of 0, 0, 0, 1, square root of 1, 1, 1, 4, square root of 4, or 2, 9, square root of 9, or 3. So what they're doing is they're cleverly picking input values such that the output values are nice numbers. Who's next? 16. Square root of 16 is 4. When we get up here to the level of 6, we'd have to put in what? 36. Square root of 36 is 6. They seem to indicate that what we have is an increasing function. They give us an arrowhead to sort of indicate the direction off into which the graph heads. But when do we get as high as 6? And this function continues to increase. My argument's about to be, it does so rather slowly though. We'd have to go out to 36. Here's 10 units. There's roughly another 10, roughly another 10. We reach 36. Somewhere over here, I think we're probably off the page by the time we reach 36, and we get out a y value of 6. So we reach a height of 3 here, we reach a height of 4 here, 5 wherever 25 appears. 6 somewhere over here. It's continuing to get larger and larger without bound, but it's doing it pretty slowly. It doesn't have a horizontal asymptote. It takes on all y values that are greater than or equal to 0, as we'll discuss. You just might have to put in some really big x values to get some of these y values out. To get out 10, we'd have to put in 100, for example. The square root of 100 is 10. So they plotted these 4 points. We will take it that the graph has those properties reflected by this tiny little graph and my additional discussion. Domains and range. We'll go through and analyze these by finding domains and ranges, intercepts, some symmetries maybe. Domain and range. What can you put into a square root function? And here, any non-negative number, any non-negative real number, you may take the square root of. You can't put negative numbers in because we're not doing that. They give us complex numbers out. Not that I got a personal problem with complex numbers, but the rules we're playing by at this stage, you can't take square roots and negatives. 2 things you can't do that might arise. You can't take square roots and negatives because I won't let you. And you can't divide by 0 because nobody can divide by 0. That's not a thing. So the outputs, the inputs start at 0, and for any x value greater than or equal to 0, I can take the square root and get a real number out. How about the range, the y values? We don't ever get negatives out of a square root function. We've said this in passing several times. Square roots are never negative. The square root of 9 is positive 3. Though true, if you square either positive or negative 3, you'll get 9 back out, but that's not the meaning of the square root symbol. The square root symbol means take the non-negative square root. So the square root of 9 is 3, not negative 3. Negative square root of 9 is negative 3. So we can get any y value out greater than or equal to 0. Any non-negative real number is also an element of the range. You don't get negative numbers out. Anything up here, you might have to wait a while, but any y value here, you will eventually reach that height by extending the graph. So domain and range are both all non-negative real numbers. The x-intercept of f of x equals the square root of x is 0. It crosses the x-axis right there. It also crosses the y-axis right there. So the x-intercept is 0, as is the y-intercept. We're shifting notation here a little bit, writing the x-intercept as the x value at which the curve touches or crosses the x-axis. Before we had expressed it as a point, 0, 0. You want to continue expressing it as a point, I'm fine with that. But in this section, at least, we'll express x-intercepts as x values and y-intercepts as y values, as the claim here is made. The y-intercept is also 0, y equals 0, because that's the only place it touches either of the axes. All the action other than that single point on the axes, all the graph, all the action occurs in quadrant 1, where both x and y are positive, with the exception of the origin. The function is neither even nor odd. Okay. If it were even, it would have a symmetry with respect to the y-axis, and there's nothing over here to be a mirror image of what's over here. So it doesn't have that symmetry. Symmetry with respect to the x-axis. A function will never have that symmetry unless it's the constant function, f of x equals 0. But there's nothing up here that I could fold over to see a mirror image of it down here. If there was, it wouldn't be a function because it would violate the vertical line test. And there's no symmetry with respect to the origin. What occurs over here for symmetry with respect to the origin, we'd have to have a related behavior down here in the third quadrant, and there's nothing down here in the third quadrant. So this has none of the 3 symmetries we normally check for, telling you the function for one thing is neither even nor odd. We'll look at even and oddness in terms of symmetries if we have graphs. And the point is we're figuring out graphs or being told graphs in this section. The function is increasing on the interval 0 to infinity. Yeah, it gets bigger. and bigger and continues to increase. It does it more and more slowly, but it does continue to move upwards. So it's an increasing function on the open interval from 0 to infinity. If you want to include that endpoint and say it's increasing on the interval including 0 to infinity, can't argue with that. That's not how we define it in here, but that's how you would deal with increasingness in calculus 1. So what I present in the notes, I'll adhere to our definitions, though you may see these a little bit different in calculus. We've only defined increasingness on an open interval, so leave the 0 out to follow this book's notation. Maxes and mins, we'll also consider, has an absolute minimum of 0. It doesn't have any output values less than this, nothing lower. And it doesn't have an absolute maximum. It increases without bound. There isn't a maximum value which the function attains. So there's some properties of the square root function. As we'll see when we dig into this in a little more depth, this is half of a parabola. You probably dealt with parabolas in your previous travels. This is half of a parabola, it turns out. How about the cube root function? We dealt with square roots, let's do cube roots. Let's plot some points. Here they've plotted 0, 0. The cube root of 0 is 0. They've plotted 1/8, 1/2. Cube root of 1/8 is 1/2 because 1/2 times 1/2 times 1/2, that's 1 over 2 cubed. 2, 4, 8, that's 1/8. That's right. Cube root of 1/2, sorry, cube root of 1/8 is 1/2. Cube root of 1 is 1. Cube root of 2, I don't know why they did this. The cube root of 2 is, well, it's cube root of 2. Okay, it's bigger than 1. I'd actually have to really work at that or just ask a calculator. Roughly, how big is that? What's the next clean number to plug in? It'd be 8, wouldn't it? If we plugged in 8, the cube root of 8 is 2. They didn't extend the graph that far, but the next nice point would be 8. We'd plug in 8, we'd get out 2, we'd have a point somewhere here. This is another one that's going to continue to grow without bound, and it's going to grow slowly. Negatives. We can take cube roots of negatives, can't take square roots of negatives, but we can take cube roots of negatives. The cube root of negative 1/8 is negative 1/2, because negative 1/2 times negative 1/2 times negative 1/2, negative 1/2 cubed is negative 1/8. So we get the point negative 1/8 comma negative 1/2 on the cube root function. Negative 1, negative 1, negative 2, negative cube root of 2 occurs over here. Of course, the next nice point would be negative 8, negative 2, which put us somewhere over here. So we're trusting them that this pattern continues. I'm not entirely sure why they wanted to graph the 1/8, 1/2. Of course, I just took the figure straight out of the book. One thing that's happening here is the function is coming in rather steeply as it comes into 0. If we were to read it in this direction, right? If we looked at it in some sense like that, it's very steep right here. All I can think is they're trying to illustrate that. Yeah, you know, the square root function has that kind of property as well. It comes in very steeply here. Steepness of a curve, steepness of a function is something you'll address in calculus 1. And they haven't reflected that behavior here so well, but they have for the cube root function. But the square root function behaves in a similar way. You might be thinking, oh, I bet you that's a part of a parabola as well. Strictly speaking, it's got a similar shape to half of a parabola, this right-hand part of it, but it's not parabolic in shape. Parabolas are related to squaring functions, not cubing functions. And this is certainly, in some sense, related to a cubing function because it's a cube root function. But these are not parabolic in shape, though they look really similar to parabolas, half of parabolas maybe. We'll take that as the graph of the function and look for domains and ranges. So probably have to go back and forth to see all this at once. Shrink it just a little bit. Domain and range says all real numbers. Can you put any real number in? Yeah, you can take the cube root of any real number. Not a problem. Cube root of 0 is 0. Cube roots of negatives exist. Not a problem. What do you get out? Says the range is, what are the y values? The range is all real numbers. You get every y value out? Yeah. You get 3 out of this function? Yeah, when you put 8 in. No, I'm sorry. What do you have to put in to get 3 out? I was thinking of 2. You put 8 in, you get the cube root of 8 is 2. What would you put in to get 3 out? 3 cubed is what, 27? So the cube root of 27 is 3. And I say this is related to cubing. There's an interplay between cubing and cube roots. We'd have to put 27 in to get 3 out, but we get 3 out. It continues to grow, though it does it slowly, just like the square root function. Also continues decreasing. It continues in this direction. Let me be careful with my verbiage. Increasing has a very specific meaning, increasing, decreasing. But this continues upwards without bound. And if we extend it to the left, it continues downward without bound. So yeah, you get every possible real number out. You want to get real number A out, put A cubed in. Take the cube root of it, you'll get A. And that works whether A is positive or negative, by the way. We get all real numbers out of this. Intercepts. This one intersects the x-axis at the origin, and it intersects the y-axis also at the origin. The x-intercept is 0, the y-intercept is 0. Let's speed this up a little bit. How about symmetries? Well, it's symmetric with respect to the origin. Whatever happens here in the first quadrant, there's similar behaviors down here in the third quadrant. If we go over 2 and up, cube root of 2, replace both of those with negative signs. We go back to -2, and down cube root of 2, down to negative cube root of 2. So every over and up has a corresponding back and down. That's symmetry with respect to the origin. So this has that kind of symmetry, and functions with that kind of symmetry are odd functions, recall. Increasing, decreasing. This function is, read from left to right. It's going uphill really, really slowly, going uphill a little bit more quickly, now it's going uphill really quickly right around here. And it continues to go uphill. We describe this increasingness informally as the graph is going uphill when read left to right. And this one's always going uphill, though it does it slowly over here and over here. When x is large and positive or large and negative, the functions, it's still increasing, it's just doing it slowly. It's increasing everywhere. So it's increasing for all real numbers. That is, if you wanted an interval notation, there's all real numbers. The interval from -infinity to infinity. You know how I feel about the from and to thing, but that's a common way to read it. All real numbers. It's an increasing function. Maxes and mins, none. It doesn't have a highest or lowest point on the graph. It's not bounded above or bounded below. So no extrema for the cube root function. Absolute value function. Okay, I'm presenting these in the order in which the book presents them. Where we didn't start with the simplest of the functions. This one is a little more exotic, but maybe a little more simple to deal with. I mean, it just looks like it's made out of lines. Maybe it's a little bit simpler to deal with than the previous functions. The shape is more simple for sure. Absolute value, let's plot some points. Let's plug in -3, -2, -1, 0, 1, 2, 3. From that, a pretty clear pattern emerges that we've got a line here, and the graph of the absolute value function, I suspect you dealt with before, looks like this. Domain is all real numbers. You can take the absolute value of anything. I think that's come up in a previous example. The range is, here it's written in a slightly different version instead of, it's an interval, all y such that y is greater than or equal to 0. If you like, it's square bracket 0, comma, infinity. Think along the y-axis. We get 0 out and everything greater than or equal to 0. The X-intercept, well, this one touches, but does not cross, touches the X-axis at the origin, touches the Y-axis there as well. So the X-intercept is 0. The Y-intercept is also 0. Symmetries, anything that happens over here, there's a mirror image behavior over there. Imagine folding it on a sheet of paper about the Y-axis, and this would lie on top of that. So it has symmetry with respect to the Y-axis. We can also describe that symmetry as every over and up has a corresponding back and up. You replace X with negative X algebraically. To test for such a symmetry, you replace X right there with negative X. Well, the absolute value will absorb the negative sign. So we do get the same kind of behaviors. For positive X is negative X. But the easiest way is to think of it in terms of a mirror image. And certainly the left-hand side is a mirror image of the right-hand side. So it is symmetric with respect to the Y-axis. There we go. Functions with such symmetries are called even functions. So the absolute value is an even function. Other examples of even functions: x squared, x to the fourth, x to the sixth. Even powers of x produce even functions. That's the reason they're called even functions. Well, this one produces an even function as well. I don't see any 2s, 4s, and 6s related to this. Well, there's more to it than that, but x squared, x to the fourth, x to the sixth are examples of even functions. That's why they're called even functions, but not all even functions necessarily need to involve even exponents. This one doesn't have any exponents, and it's an even function. Extrema, is that next? Oh, increasing and decreasing is next. All right, where's the function going uphill and downhill? Reading from left to right, it's going downhill and then uphill. So it's decreasing in terms of x values. It's decreasing from negative infinity to 0, and it's increasing from 0 to infinity. That is, it's decreasing on the interval negative infinity, comma 0, parentheses, not a square bracket. In calculus, you'll put a square bracket there. So I'm okay if you want to use square brackets here, as long as 0's in the domain. That would be consistent with calculus notation. So just giving you a heads up that our notation is a little bit different when we discuss increasing and decreasing. Then it switches to increasing at 0, and it's increasing from 0 to infinity. Decreasing on the left, increasing on the right. Extrema, does that have a lowest point on the graph? Yeah, that one. So the minimum is 0, y equals 0, f of x equals 0, at x equals 0. So these two zeros, one's an input, one's an output, one's a where, one's a what. What's the minimum? 0. Strictly speaking, it's that 0 because it's the y value. Where does that occur? At x equals 0. Strictly speaking, that 0 because it's an input value. About maxes, it doesn't have a maximum. It's unbounded above. Absolute value function. About a constant function. Functions don't get much easier than this. Suppose f of x equals b. Then we'll go to the point 0, comma b and draw a horizontal line. No matter what you put in, you get out b. There's what this function looks like. Here's an illustration in the event that b is positive. If b is 0, the graph would be the x-axis. If b is negative, we'd have a horizontal line still. It'd just be below the x-axis. So what's the domain? We plug any number you want in for x. You're going to get b out of this function. But what could go wrong? Division by 0 and square roots of negatives. No division, no square roots. Not even any x's in the definition of the function. So nothing will go wrong. The range is all real numbers. The domain is all real numbers. The range is the output values. What y values do you get out? Well, one of them, b. The only value you get out of this function is b. No matter what you put in, it gives you b back out. So the range simply consists of the single number, the set, consisting of element b. X-intercepts, well, there aren't any, unless b equals 0, and we're considering f of x equals 0. Then you get the x-axis out. Well, if that's the case, every number every point is an X-intercept. In terms of Y-intercepts, it crosses the Y-axis at that point 0, b, the only Y value that it gives out. To find the Y-intercept, you'd set X equal to 0. So you get X is 0, Y is B. As I said, we're mostly expressing intercepts in terms of X values for X-intercepts, Y values for Y-intercepts. Even symmetries, yeah, symmetric with respect to the Y-axis, folded over, the right-hand side would lie on the left-hand side. That's symmetry with respect to the Y-axis. Functions with that symmetry are even functions. So this is an even function. Increasing, decreasing, it's constant. It's a constant function. So it's constant on the whole real line, though neither increasing nor decreasing. Maxes and mins, it's B. The biggest it is B. The least it is B. Everything is B. The maximums, the minimums, everything is B. The max is B, the min is B for a constant function. Okay, let's look at one a little more interesting. Maybe less interesting, it's less complicated, but one you're more likely to encounter. Adjust my equipment a little bit here. Okay, we're going to consider f of x equals x. Plug in 0, get out 0. Plug in 1, get out 1. Plug in 2, get out 2. Plug in 3, get out 3. Plug in -1, get out -1, blah, 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 blah. Why they only plotted 3 points, I don't know. Unless you already know that's a line. If you know that's a line, then we're in business. I guess we dealt with lines in what, section 1.3. So you do know this is the graph of a line of slope 0, and I'm sorry, slope 1, m equals 1, and y-intercept 0. Knowing it's a line, I don't really need but 2 points. But anyhow, we get the line y equals x by plotting points. This you already knew. I may say you're not that great at graphing in Precalculus 1. We're doing our best. But you're good at graphing lines. Lines, you've got lines. You got circles as well. So you're good at graphing lines and circles. We're trying to make you good at graphing some other stuff by adding other things to the library of functions. But anyhow, graph of f of x equals x looks like this. That really you already knew. Domain, all real numbers. Anything goes in. Range, all real numbers. Anything comes out. X-intercept, Y-intercept, right there. X-intercept is 0, Y-intercept is 0, speaking in terms of X and Y values, as we've started to do. Odd function. Symmetric with respect to the origin. Yeah, every over and up point on the curve, there's a corresponding back and down. You go over 3 and up 3, point on the curve. You go back 3 and down 3. There's a point on the curve. So it is an odd function. In that sense, it's symmetric with respect to the origin. Functions with that symmetry are called odd functions. Let me shrink it for the last part of the conversation. You see any odd numbers there in the definition of that function? Yeah, it's x to the first power. It's x to the 1, and 1 is odd. So this one is related to a power of the variable in that oddness. Don't exclusively think that even and odd require powers of variables to be even or odd. But when you do only have x to an even or odd power, then I guarantee you've got an even or odd function respectively, which is the case in this one. So symmetry with respect to the origin, odd function. What else? Increasing and decreasing, it's always increasing. Read from left to right, it's always going uphill. And in terms of extrema, there's no lowest point or highest point on the graph of this. It's unbounded below and above. So this one has no absolute max and no absolute min. I mentioned this just in passing. You wouldn't say infinity is the maximum because there isn't an infinity. This function doesn't take on the value infinity. That's not even a number. It takes in real numbers and it gives out real numbers. It doesn't have a maximum. don't say the maximum is infinite. That's not how numbers work and not how functions work. Another example, let's go through these powers of x. X squared. 0, 0, 1, 1 squared, 1, 1, 2, 2 squared, 2, 4, negative 1, positive 1, negative 1 squared is positive 1, negative 2 squared is positive 4. The even exponent will absorb the negative signs. And what's up with this? I plug in 3, I get out 9. I plug in 4, I get out 16, right? It outgrows the page pretty fast. So I understand why they only plotted these few points in this one. And you probably dealt with these before. We'll deal with them some more in upcoming chapters. But y equals x squared, f of x equals x squared, looks like this. What can you plug in? Anything. I can square any real number, not a problem. What do you get out? Well, when you square something, it's not going to be negative. Could be 0. 0 right there. Plug 0 in, get 0 out. Anything else, it's going to be positive. Domain is all real numbers. We can square everything. Range starts at 0 and includes everything greater than 0. The range is a set of all non-negative numbers. We could express that in interval notation, and we could describe it as a set, if you like. And we did that in one of the previous ones. So domain and range. Intercepts, both 0. X-intercept 0, Y-intercept is 0. It's the only place it touches the x-axis and the only place it touches the y-axis. I guess it crosses the y-axis. So both intercepts are 0. Even, it's an even function. It's symmetric with respect to the y-axis. Fold it over, left-hand side, right-hand side would then coincide. That's evenness. Oh yeah, it's got something to do with that evenness of the exponent, x squared, 2 being even. Increasing and decreasing. Read from left to right. I always say that. It's easy enough to slip and start in the middle and look one way and the other. Reading from left to right, it goes downhill, decreasing, and then it goes uphill. So it's decreasing for these x values. That would be negative infinity to 0, and it's increasing from 0 to infinity. Expressed as intervals. There's where it's decreasing. There's where it's increasing. You know the story about including the endpoint. We won't do it in here in calculus. In this exact same situation, you would include the 0 in both of those intervals. The function has an absolute minimum at 0, right? I still see that on the screen. It's unbounded above, continues without bound, so it has no absolute maximum. F of x equals x squared. How about x cubed? So f of x equals x cubed. Really wish they would have plotted a couple more points on this. They plotted 3 points. Those 3 points are collinear. I could draw a straight line through those. The line y equals x passes through those 3 points. So we need more information than 3 points to get an idea of what's going on here, really. But were we to plug in 2, we'd get out 8. So we get out a point somewhere up here. If you plug in -2, you get out -8. So it's going to grow really quickly. It's going to grow a lot faster than a y equals x function. If you plug in 4, you get out 4 cubed. What's that? I think it's 256. So I see why they didn't go too far to the right, but I do wish they'd have given you at least another point over here, maybe 2, 8, and -2, -8. And the graph looks something like this. And it extends onward without bound. That's what the little arrows are meant to indicate. Domain, which numbers can you cube? All of them. Domain is all real numbers. The range, what numbers do you get out? It looks like you get out all y values. It increases without bound. Do you get out a y value up here? Yeah, it's going to continue to increase and at some point cross this level, which corresponds to a y value. Same thing happens below. All real numbers are in the range of the function. Intercepts, again, x-intercept is 0, y-intercept is 0. Crosses both axes right there. Symmetries, over and up, there's a corresponding back and down, and that holds for all points on this. If you think about folding it over, right, we'd fold this thing in the first quadrant over into the second quadrant and then fold it down, and it would lie on top of this. We described this in terms of smiley faces in the past. And indeed, this is the kind of symmetry you have when you have symmetry with respect to the origin. We computed it in terms of replacing an over with a back and an up with a down. Replace x with negative x and y with negative y was the algebraic way of dealing with it. But since we have a graph, we can look at the graph and see it does the same thing in the first quadrant in a mirror image style that it does in the third quadrant. And similarly, it does the same thing in the second quadrant that it does in the fourth quadrant, namely nothing in this example. But this is symmetric with respect to the origin. And so this is an odd function. Oh yeah, it's x to the third power. So the fact that 3 is odd has something to do with that. That's the reason these are called odd functions again. Increasing and extrema, it's read from left to right. It's always going uphill. Going really, really steeply uphill, it seems. It looks like it might level off and then it goes uphill some more. This is a function that's increasing everywhere. Extrema, it's unbounded below, it's unbounded above. There's not a lowest point or highest point on the graph of this function, so it has no max nor mins. Absolute nor local for that one. 1 over x. Let's look at the graph of that. Okay. I'm a little disappointed again. This time they plotted 4 points. You probably have some experience with 1 over x as a function. Think like this. If x is a big positive number, like 10 or 100, then its reciprocal is a little positive number, like 1/10 or 1/100th. So when I put big numbers in, I'll get little numbers out. Big positive numbers give little positive numbers out. So what this curve is going to do is it's going to level off and asymptotically approach the x-axis on the right. A little premature to talk about asymptotes, vertical or horizontal, but we will before we're done. And you probably have an intuitive feel for that. If I plugged a big negative number in, like negative 100, we'd get a very small negative number out, like negative 1/100th. So similarly over here, it's going to get closer and closer to the x-axis and never get there, though that's not what a horizontal asymptote is. More of that later. But it gets close and it never gets there. That is the case for this graph. What happens when you plug a little tiny positive number in? Let's plug in 1/100th for x. Well, then you'll get out 1 over 1/100th. You'll get 100 out. So when you put little numbers in, little positive numbers, you get big positive numbers out. When you plug little negative numbers in, you get big negative numbers out. So you know what this is going to look like. It's going to have a vertical asymptote. It's going to get closer and closer, but never get there to the y-axis. Get closer and closer, but never get there to the x-axis over here on the right. And similarly, asymptotically approach the y-axis from this side and asymptotically approach the x-axis towards the left. So that's what the graph of the 1 over x, the reciprocal function, looks like. I could have used more than 4 points, but I think you have experience enough to find it plausible, these ideas that I've drug into the conversation. Domain, what can go wrong? Square roots and negatives, no square roots. Division by 0, because there is division. X can't be 0. Other than that, you're good. So the domain is all real numbers except for 0, written in interval notation using the union symbol as given there. We discussed interval notation and the union idea in one of the appendices. What about the range? Can't get 0 out of the function. 1 over nothing equals 0. So there's no y-intercept when we deal with intercepts. So we don't get y values out, but anything a little bit bigger than 0, there'll be an x value that will produce that y value. Anything a little bit less than 0 or a lot less than 0 or a lot greater than 0. We can get anything out of this function except 0. So the range is also negative infinity to 0, union 0 to infinity. You can include those zeros there, right? This is not increasing, decreasing conversation. This is domain. This function isn't defined at 0. You can include 0 in these intervals. So there's a domain and range. I mentioned just in passing, you know, the shape, what shape this is called? Do you believe it's a hyperbola? You've dealt with conic sections before. The graph of this function is actually a hyperbola. But we don't need that. We actually won't address that in Precalculus 1. You will in Precalculus 2. And you'll see these ideas again in calculus. There's neither an X-intercept nor a Y-intercept, right? X isn't in the domain. I'm sorry, X equals 0 is not in the domain. Y equals 0 is not in the range. We can't put 0 in. We won't get 0 out. So no intercepts. The function's odd because it has symmetry with respect to the origin. Yeah. Each over and up has a corresponding back and down. This point here, over 1/2 up 2, corresponds to which point? Back 1/2 and down 2. It'd be a point right here. This point corresponds to a point right here in terms of symmetry with respect to the origin. So they haven't drawn corresponding points. The 1 over 1 up corresponds to the 1 back, 1 down. Those 2 points do correspond. These 2 do not. This point corresponds with the point down here. This point corresponds, this was a back 2 and down a half. This would be over 2 and up a half. It corresponds to the point right here. This point corresponds with the point where that arrowhead is. So they haven't drawn corresponding points in what they've drawn. But it has that kind of symmetry with respect to the origin. And so this is an odd function. You see an odd number in this one as an exponent? You know, maybe. We could write 1 over x is x to the -1. -1's an odd number. So that's not a coincidence that this is an odd function and it's an odd power of x. -1 counts as an odd number as well. Extrema, decreasing, increasing, read from left to right. Oops. Make the picture a little bit bigger again. Read from left to right, it goes downhill, downhill, downhill very shallowly, but downhill, 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 downhill. It's going downhill everywhere, except at 0 where it's undefined. So this is a decreasing function on its domain. So it's decreasing on the interval, negative infinity to 0, throw 0 out because it's not defined at 0, union 0 to infinity. You can't include the endpoints here. The function's not defined at 0 here. Here, you have to use the parentheses and the open intervals. Function's not defined at 0. It can't be decreasing there. And extrema, it's unbounded above and below. So it has no absolute max and no absolute min. Let's look at the greatest integer function. Okay, this one's a touch more exotic than the ones we've dealt with. The greatest integer function denoted int of x. Sometimes it's denoted with these little brackets that have the little hash marks at the bottom. You're rounding down. That's the reason there's little hash marks at the bottom. If the hash marks were at the top and not the bottom, then you'd round up. So this is a rounding down function. The common term, and you'll see this function in calculus as well, is a greatest integer function. For example, if you put an integer in, it's going to give that integer out. If you put a non-integer in, like 2.5, it's going to round down. It finds the largest integer less than or equal to the input. So you put 2.5 in, what's the largest integer that's less than 2.5? 2 itself. It truncates the 0.5. You put 1/2 in, it rounds it down to 0. Straightforward, rounds down. And it does the same thing with the negatives, but they look a little different. This is consistent, totally consistent with what we just discussed. It takes -3/4. rounds it down to the greatest integer less than or equal to -3/4. That's -1, not 0. Rounds it down to -1. -2.5, it rounds it down to -3. So the behavior at the positive numbers and the negative numbers is consistent, but it's a little tricky. That's the reason I listed these by these particular examples. It gives you the greatest integer less than or equal to. It rounds down. You round -2.5 down, you round it down to -3. -2 is bigger than this. This is rounds down, not up. So f of -2.5 is -3. It's consistent with the other values. It's just a little bit easier to see with the positive values and a touch tricky with the negative values. They claim the graph looks like this. Let's look at that in a little more detail. They've plotted some points here. Their pattern has been, the stuff in black is the points they've plotted. They've plotted this for integer values. Notice if you just had the information given by the black points, this looks like the line y equals x. Now, y equals x contains all of those black points, but it isn't the same as the greatest integer function, because what does the greatest integer function do to all the numbers between 0 and 1? It rounds them down to 0. At 1, it takes on the value 1. What does it do to all the numbers between 1 and 2? Excluding 2, it rounds them down to 1. It rounds them down. It truncates, in a sense, the decimal part. Similarly over here, what's it do to all numbers between -1 and 0? It rounds them down to -1. The output value here is y equals -1. Output value here is y equals -2. You might also see this call, for obvious reasons, the step function. So it looks like a sequence of steps. Passes the vertical line test, right? Yeah, if we look here, vertical line, say through x equals 2, intersects a curve at one point, that point right there. Not there, that's why there's a little open circle there. So it really is a function. And the domain is a set of all real numbers. You can round any real number down. The range, well, when you round down, you're going to get an integer out. Then you can get any of the integers out. That's certainly suggested by the figure given here. So the range is a set of integers. We've mentioned probably in the appendices that the integers are denoted with a Z. This is a Blackboard font, it's called. But here's the integers. Yeah, any positive or negative or 0 whole number we can get out of this function. Intercepts. Let's see. It touches the x-axis at all these points here. That's every x value between 0 and 1, including 0 and excluding 1. Look at the dark circles versus the open circles, the shaded in circles versus the open circles. So not 1 itself, but everything else between 0 and 1, including 0. So x-intercepts include 0, excludes 1, and everything in between is included. Y-intercept, if it's a function, it's only got one y-intercept. There it is right there where it crosses the y-axis. The y-intercept is 0, as it says here. Even or odd, any of the symmetries, it's not symmetric, certainly not symmetric with respect to the y-axis. Things that happen over here would have corresponding steps over here, and it doesn't have that. Now, there is stuff in the first and the third quadrant, but they're not corresponding. If I go, say, over 1.5 and up 1, I find a point, 1.5, 1. Well, if it has symmetry with respect to the origin, I can go back 1.5 to -1.5 and down 1 and find a point on the curve, but there's not a point on the curve. When you apply the greatest integer function to -1.5, it rounds it down to -2. Here's the -2 y value. So this point, if it had symmetry with respect to the origin, there would be a corresponding point here, and there's not. It's down here. So it doesn't have symmetry with respect to the origin. we could create a graph based on what's in the first quadrant. What we do is we'd pick up extending this over to -1. We have to shift all these steps back 1 unit. But that's not what the function is. So it doesn't have that kind of symmetry. So it's neither even nor odd. So none of those symmetries. Increasing, decreasing. Well, the way we've defined increasing and decreasing, this function it's constant. It's constant on these little intervals where it's defined. It looks like it's increasing. There's some kind of uphillness to it, but it's constant on the little steps. Where there's discontinuities, where there's a little gaps, and that's where it goes uphill. But the way we've defined increasing and decreasing this function has to be described as a function that's constant on the little steps. So the function is constant on intervals of the form n to n plus 1, where n's an integer. It includes the left-hand endpoint and excludes the right-hand endpoint, as indicated by the colored in dots on the left and the open circles on the right. Maxes and mins, it's unbounded. The range is the integers, it's unbounded. There's not a highest point or lowest point on the graph, continues without bound in both directions, so no extrema. You like this function? It's not continuous. You can't draw it without picking up your pencil. Continuity is a much more involved concept than picking up your pencil. That'll have to do in here, though. You'll address it in Calculus 1. It's got these little gaps in it, so it's not a continuous function. Were any of the others we dealt with, were they not continuous? I think there might have been. They weren't like this, though. That function's not continuous. I can't draw it without picking up my pencil. There's a piece of it over here and another piece of it over there because it's not defined at 0, the 1/x function. No problems there. That one's continuous. Squaring function's continuous. I think the rest of them were. F of x equals x is continuous. Constant function's continuous. Absolute value function's continuous. We had the cube root, continuous. Square root, continuous. It's not defined everywhere, but where it is defined, I can draw it without picking up my pencil. So in terms of continuity, just to bring it up in passing, we will talk about it as best we can later. Where were we? That function's got a lot of points of discontinuity. Wherever it steps up, there's a point of discontinuity. So you might interpret that as somewhat of an exotic function because of the discontinuities. How many functions do you see here? 1. Its name is, we gave it a couple of names. Its name is either f or int of x, or this little bracket notation. There's one function there. It comes in a bunch of pieces. We're segueing into piecewise-defined functions, but this represents a single function. It just comes in a bunch of pieces. Speaking of, when a function is defined on different parts of its domain, it's called a piecewise-defined function. So what we're going to see, similar to that greatest integer function, is when we deal with piecewise-defined functions, we're getting a single function, but it comes in pieces. There might be 3 pieces to it, but that's just one function. I bring this up because I see this as a common misconception. Here's a piecewise-defined function, example 3 from the book. Consider the function f of x defined piecewise as follows. It's -2x plus 1, provided x is between -3 and 1, including -3 and excluding 1. It's the value 2 when x equals 1, and it's x squared when x is greater than 1. How many functions do you see? 1, f. It's got, looks like 3 pieces, but there's only one function, and its name is f. Which piece do you use? Well, that depends what you input. If you input a number between -3 and 1, including -3 and excluding 1, you use that piece. If you put in 1, you use this piece. Plug in a number bigger than 1, You use that piece. What if you try to plug in a number less than -3? Well, it's not defined there. That's not in the domain. It's defined where they've defined it. They've defined it from -3 to 1, 1, and then values greater than 1. To further illustrate that, find these values. Plug in -2, 1, and 2. What function values do you get? Which piece do you use? F of -2. To find f of -2, do you use that piece, or that piece? Well, where is -2? It's between -3 and 1. -2, when x equals -2, it satisfies that first inequality. -3 is less than or equal to -2 is less than 1. It's in that interval. So use the first piece. So we use the piece of f defined as -2x plus 1. So f of -2, because -2 satisfies this condition as an x value, we use this piece. Don't use that piece, don't use that piece, not when x is -2. Maybe you use it some other times. So f of -2 then is plug in -2 for x. So the only thing that makes this complicated is you got to make a choice on which piece to use. And you're told over here, based on the x values, which piece to use. So plug -2 in for x, the appropriate piece, based on the x value. And we get -2 times -2 plus 1, simplifies to 5. F of -2 is 5. How about the other pieces? 1. Well, plug in 1 for x. But in which piece? X equals 1, use this piece. We plug in 1 for x and we get out 2. No x is there for me to use. When x equals 1, you get out the value 2. F of 1 is 2. F of 2, where does 2 live? It's not between -3 and 1. It's not 1. It's this one. 2 is bigger than 1. So use this piece and plug x equals 2 into that piece. So f of 2 is 2 squared, and that's 4. Piecewise defined functions are not that complicated. I've seen some troubles with these in the past. Just do what it says. You don't plug -2 in all 3 pieces of those. When they ask for -2, you plug it into the correct piece. You're only going to get one number out because it's a function. Functions take one good number in and they give you one number out. You only get one number out of this. This is one function. It comes in 3 pieces. It's not 3 functions. It's one function defined in 3 pieces. Secondly, what about the domain? Intercepts, graph, range. Is it continuous on its domain? Finding ranges is hard unless you've got a graph. We'll graph this. You know how to graph this piece. That's a line with slope -2, y-intercept 1. You know how to graph that. There's a point. And you know how to graph y equals x squared, don't you? You do now. It's in your library of functions. So this is how we're using the library of functions. So part B, determine the domain of the function. Okay, domain of f would be where the function's defined. It's defined between -3 and 1, including the -3 and excluding the 1. Right there is the definition of it for those x values. It's defined at x equals 1, so it'll include the singleton 1 set consisting of a single element. It's defined for x greater than 1. So that would be an interval notation, 1 to infinity. We will union those up. Again, interval notation and unions and intersections are reviewed in the appendices. Paste those 3 together. This includes everything from -3 up to 1. Then this includes the 1, and then this includes everything greater than 1. Glue those 3 intervals together, those 2 intervals in that singleton, and you get the interval from -3 to infinity, including the -3. That's the domain of the function, because that's where it's defined. They defined it exactly there. So I'm shifting gears a little bit on my what can go wrong, because we're learning more stuff. I don't just look for division by 0 and square roots of negatives. I mean, that's still an issue, but now they've told us exactly where the function's defined. So presumably they haven't introduced any division by zeros and square roots of negatives in so doing. But where's the function defined? Where they defined it. I take those pieces, the intervals on which the function is defined in pieces, union them together, that's the domain of the function. What's the range? Not yet. I need a graph for the range, but we found the domain intercepts. All right, we got 3 pieces to consider. So we want to first set x equal to 0, and we'll find an x-intercept. Or sorry, find a y-intercept. For the y-intercept, set x equal to 0. Plug in 0 for x, f of 0. Which piece do you use? 0's in here, so we'll use this piece because x is 0. We'll get -2 times 0 plus 1, -2 times 0 plus 1 equals 1. There's the y-intercept. Set x equal to 0 to find the y-intercept. X-intercept could have multiple x-intercepts. A function will have only one y-intercept, right? It's got to pass the vertical line test. Could have none as far as that goes. X-intercepts, a function could have a lot of x-intercepts. So it depends on the function. The sine function has an infinite number of y-intercepts. I'm sorry, x-intercepts, for example. So for x-intercepts, we'll set y equal to 0, but which piece are you going to use? We have to check each of them. We'll check each piece of the function, set that piece equal to 0, and solve for x, and see if that's a point on the graph. First, take the piece -2x plus 1. -2x plus 1. Notice this is only good for x between -3 and 1. But let's take that piece, set it equal to 0. Solve for x, you get x equals 1/2. Is 1/2 in the interval on which the function looks like that? It is. The function looks like that on this interval. This interval contains 1/2. It is a point on the graph. Plug in 1/2, get 0 out. That's an x-intercept. So x equals 1/2 is an x-intercept. Second, look at the second piece. It was just 2. Set 2 equal to 0. Well, I don't care what x is. 2 doesn't equal 0, so that doesn't happen. But we're doing the same protocol. We set x equal to 0. Sorry, we set this equal to 0. Set the function equal to 0. Y equals to 0. And solve for x. And it worked. Next, set this piece equal to 0. When you set 2 equal to 0, that's meaningless. So that doesn't work. Thirdly, we'll set this piece equal to 0. And remember, you only use this piece when x is greater than 1. Back down to the computations. So we set 2 equal to 0. That's meaningless, so that doesn't give any intercepts. Thirdly, we'll set x squared equal to 0. If x squared equals 0, then x equals 0. But when you plug x into the function, x equals 0 into the function, you don't use this piece. This piece was only valid when we had x values between 1 and infinity, and 0's not between 1 and infinity. So if you plug 0 into the function, you're not going to see this. 0 doesn't go into x squared. 0 goes in something else. So based on the piecewise-defined nature of the function, we do get x squared equals 0 when x equals 0. But you don't use x squared when x equals 0. You use something else. So the function f itself is not 0 when x equals 0, because that's not what the function looks like when x equals 0. It looks like one of those other pieces. So this doesn't yield an intercept. We set the function, we set y equal to 0, the function value equal to 0, and we didn't have a solution to function equals 0, because when the output value we saw was x equals 0, that's not what the function looks like. So the equation gave us a solution, but the function doesn't. You might want to think on that, pause for a second, scroll back up in the notes, and look at the piecewise-defined nature. If you set the function equal to 0, then I need to check these 3 pieces. And the output I get needs to be in the appropriate interval for it to count as an intercept. It worked fine in the first one. It was nonsense in the second one, and it kind of looked like it worked in this one, but we got x equals 0. But this is not the function when x equals 0. When x equals 0, this is this part that you use. So you plug 0 into the function, you don't get 0 squared out. You get -2 times 0 plus 1. We saw that earlier when we were doing some X-intercept stuff. Or was it Y-intercept stuff right there. So you might want to pause this and think about that in terms of the piecewise defined function. We only found one point that worked. That was y equals 0 implies x equals a half, even though some other noise was going on in the background. In the end, it didn't count because of the x value it outputted. That wasn't the piece of the function we would use for that x value. Graph it, they said. Okay, well, we know what the pieces look like. -2x plus 1, graph y equals that. That's a line with slope -2, y-intercept 1. But that's only valid on the interval from -3 to 1. All right, so we'll graph the line for those x values, excluding 1. I'll put a little hole in the graph. Then we'll graph the middle part. When you plugged in 1, you got out 2, was the center piece of the graph. And then we'll graph the squaring function, x squared. You know how to do that now because it's in the library of functions. But we'll only do that for x greater than 1 because the function only equals x squared for x greater than 1. So for these x values, we'll graph that. For x equals 1, we'll have the point 1, 2. For these x values, we'll graph this and paste those three things together as appropriate. We'll put them on one graph, I should say. Alternatively, you might think of it as, well, we'll graph this line and then erase all of it except for the part that corresponds to these x values. We'll graph this x squared function and erase all of it except for the part that corresponds to x greater than 1. Ultimately, it's the same thing. Okay, so we were dealing with 2x plus 1. Negative 2x plus 1. Get my story straight here. Negative 2x plus 1. All right, for x between -3 and 1, including -3. So we could plot x equals -3 times 2 plus 1 times -2. Let's try that again. X equals -3. We're dealing with f of x is -2x plus 1. -2 times -3 plus 1 yields a 7. So input the -3 into the first part, input -2 into the first part, input -1 into the first part, 0 for the first part, 1. Actually, you don't put 1 into the first part because the first part is no longer valid at 1. I really only need 2 points, though, to determine the line. So this is a bit of overkill. They've indicated this one probably to discuss the X-intercept that we had above. And take those points, connect them with a straight line segment for x starting at -3 and going all the way up to -1, but excluding -1. So the fact that that piece was only valid for x between -3 and 1, including -3, solid circle there, excluding 1, open circle there. That's the first piece of the graph. Second piece, when x equals 1, f of x equals 2. It's that single point right there, the point 1, 2. The third piece was the x squared part. So what you might do is plot a nice little x squared parabola here, but then go through and erase it where it doesn't count. It only counts for x greater than 1, strictly greater than 1. So we have to put a little open circle there for the strictly greater than 1 part. And this is what you get. It passes through the point 2, 4. It passes through the point 3, 9, they were to plot it, it'd be somewhere around here. So you're getting a parabolic shape here, piece of it at least. We've erased a bunch of it. The part of it that would correspond to x less than or equal to 1. We've erased this left-hand side of that parabola. Here's the first piece, it's a line. Here's the second piece, it's a point. Here's the third piece, it's part of a y equals x squared. I should say it's a part of a line, a point, and part of a y equals x squared. This is a single function. It comes in 3 pieces. The first piece, the second piece, and the third piece. The negative 2x plus 1 part, the 2 part, and the x squared part. Sure, this is a function. Does it satisfy the vertical line test? Yeah, we were real careful there. At x equals 1, this point's not included, this point's not included, this point is. So it satisfies the vertical line test. If I color in either of these 2 points, then we fail the vertical line test and it's not a function. So they were careful in their definition of it. Range, they want the range. All right. What y values can you get out? Let's see, we're good with big Y values. They'll be produced by this thing that continues onward. So we've got everything up here, everything here. Actually, these things we're getting out twice. 5 you get out over here, and you get it out somewhere over here as well. But anyhow, you get 5, the value 5 out. We're still getting all those Y values. Right there, we get the Y value of 2 out 3 times. There, and there. We continue down, we're still getting Y values out, We only get them out of the negative 2x plus 1 part down here. Y values down to 0. And you don't get the Y value negative 1 out. Negative 1 along the Y axis, you don't get that out because it's a little open circle. And I continue sweeping the cursor back and forth, looking for Y values. Below negative 1, there's nothing drawn. So up here, values, missed that one, and everything below it. So anything strictly greater than y equals negative 1, all real numbers greater than negative 1, are outputs of the function. That is, in interval notation, the range of the function is negative 1 to infinity. Geez, we found the domain easily. Yeah, domains are usually pretty easy to find. For piecewise defined functions, you just see where it's defined. For functions defined by a formula, we look for bad stuff, like square roots of negatives and division by 0. Ranges, we don't have an algebraic way of finding ranges. We need a graph to find ranges. And in the past, the only time we've dealt with range, we always had a graph. So you need a graph to find the range. And we've got a library that consists of a handful of things we can graph. So we can ask a few more range questions now. We're constrained to answer range questions related to the library of functions, as we will be throughout this class. They ask about continuity. No, it's not continuous because it's got a gap in it right there. I can draw this part without picking up my pencil. Then I got to pick up my pencil and put a dot there. I got to pick my pencil up again and start drawing over here. And we get that kind of behavior. Not continuous. It's not continuous at x equals 1. It's continuous everywhere else it's defined, but it's not continuous at 1. I emphasize again, when you look at the graph, how many functions do you see? 1. There's one function. F is its name. It's piecewise defined, so it comes in 3 pieces. The line piece, the point piece, and the x squared piece. One function, 3 pieces. That's how piecewise defined functions tend to behave. Let's do some examples. So shifting over to some examples from the book. Number 28 gives a piecewise defined function. Ask you to find some function values. Okay. We'll just plug -2 in. Wherever I see an x, I'll put a -2 in the appropriate piece of the piecewise defined function. Pieces are based on x being less than -1, equal to -1, and greater than -1. Evaluate. Okay, -2. -2 is less than -1. If we take x equals to -2, then x is less than -1. When the input is less than -1, use this piece. So you plug -2 into this piece. F of -2 is -3 times -2, -3x. That's +6. 0. Which piece you're going to plug 0 into? There's a 0 right there. Yeah, but no, that's a function value. That's a y value, not an x value. X values are discussed over here. You're inputting 0 when x equals 0. How does it relate to the information on the right? 0 is greater than -1. It's this one. So this is the piece you use when x equals 0. Keep straight. You've got x values and y values. So be careful. It is easy enough to mix those up. That's the x values we're talking about. X equals 0. We'll use this part. And we'll get 2 times 0 squared plus 1. F of 0 is 2 times 0 squared plus 1. Use that piece because x equals 0 satisfies this condition. 1. Yeah, 1 is greater than -1. So similarly, when x equals 1, x is greater than -1, 1 is greater than -1. Use this piece again. So f of 1 is 2, 1 squared plus 1 equals 3. F of 3, yeah, the story's getting old. 3 is bigger than -1, so you still use that third piece. Looks like you get out 19. Piecewise defined functions, inputs depend on what the input is as to which piece you use. Let's see, same function, different problem. They start asking you different stuff. So I picked the same function for the sake of illustration. Find the domain, intercepts, graph it. Based on the graph, find the range. Is it continuous? So this is another example, just like the one we did in the notes. Domain, where is it defined? For x less than -1, it's defined. For x equals -1, it's defined. And for x greater than -1, it's defined. So it's defined for all real numbers x, unless these pieces involve division by 0 and square roots and negatives, and none of the pieces do. So that's not an issue. So nothing goes wrong. The pieces include all real numbers. So the domain of the function is all real numbers. The real numbers symbol, or think of it as the interval from -infinity to infinity. Intercepts. All right, this is the trickiest part probably of all of this. Y-intercept, set x equal to 0. F of 0 is, which piece do you use? I think we did this on the first slide. This piece, 0 is greater than -1, so use this piece. 0 is greater than -1, use this piece. 2 times 0 squared plus 1, we get out 1. The y-intercept is 1, or if you want to express it as a point, 0, 1 as a point. But that's easy enough. It's the x-intercepts that are going to be complicated. We'll have to check all three pieces. For the x-intercept, set y, f of x, equal to 0. In the first piece of f, that's -3x. Set -3x equal to 0. -3x is 0 when x is 0. But does x equal 0? X equals 0. Does this count when x is 0? No, this is only good for x less than -1. 0 is greater than -1. So it's that situation again where, yeah, this -3x is 0 when x equals 0. But when x equals 0, f is not represented by this. We had to check this, but it doesn't give an intercept because we require x to equal 0 for this piece to be 0. And this piece isn't what you use when x equals 0. It's a little tricky. How about the second piece? Set that equal to 0. The piece is 0, so this is working. You use this piece when x equals -1. So we'll have the function equal to 0 and the x value equal to -1. We do get an intercept there. The function is defined to be 0 at -1. You find x-intercepts by setting the function equal to 0. We're having to do it piecewise because of the piecewise-defined function, but it works for x equals -1, and that gives us an x-intercept of -1. Third piece, 2x squared plus 1, set it equal to 0. Solve for x and see if those x values satisfy this condition. If they do, then you got more intercepts. But hey, 2x squared plus 1, that's not 0. That's positive. This is positive. We've added 1 to it. This is at least 1. It's not 0. So there's no x values that solve this. So we don't have to get into it with that one, it turns out. So the only intercept we found was when x is -1. The x-intercept of f is -1. Okay, so here's the information we have. We've got a y-intercept, an x-intercept, a piecewise-defined function. They want us to graph it. Can you graph this piece? Sure. Line with slope -3, y-intercept 0. This is just a point, -1, 0. This thing. We've graphed squaring functions, and we know that squaring functions, we know what they look like. They're opening upwards parabolas. Now, we haven't added 1 to them and multiplied them by 2. It's actually a little bit early for them to ask us this kind of thing. We'll deal with this later when we do transformations. But just plot a handful of points and try to get an idea of what's going on with this. My apologies, because it's a little bit early to talk about 2x squared plus 1. Granted, we have dealt with x squared. It's in the library, but this is not exactly x squared. It's x squared somewhat modified. So for the sake of illustration, let's graph. We know y equals -3x. There's a line, slope -3, y-intercept 0. How about we graph that line, but it's only good for x less than -1. We could maybe plug in -2. We'd get out -2 right here. We'd get out 6. We mentioned that earlier. We had that function value earlier. So that gives us the point -2, 6. There's the point right there on the line segment. You want to plug in -1? Well, it's not defined at -1. This is, but the function's not. Well, that still makes the point x equals -1 a useful point. If we plug -1 into -3x, we get out +3. So there's the point -1, +3, that point right there. But that's not included on the graph of the function. So what we've got is this straight line. Here's 2 points on it. 2 points determine a line. This is on the line y equals -3x. I got to put a little open circle on that one because the function doesn't look like this when x equals -1. It looks like something else. But still, you might think of graphing the line y equals -3x. You plug in all the x values you want and get a nice graph of the line. But then go back and erase the thing for x values that violate this. So we might draw a line that passes through this point. It probably passes through that point. We'd have this nice little line. But then we have to go through and erase it for the bad x values. I know the graph of y equals -3x. We're just using part of it. Here's the part we're using. So this is a straight line segment. It's a little bit hard to see on the scale, I understand, but this is a straight line segment here. When x is -1, we get out 0. So we'll have the point -1, 0 on the graph. There it is right there. -1, 0. By the way, that was the x-intercept, as we discussed above. That gives us a single point there. Now we want to graph 2x squared plus 1 for x greater than -1. Let's look at that and just let's plug in some numbers. Regrettably, we've got to approach it this way because we have no other way to deal with it. This will be explored in more detail. I guess it's the next section. We'll take things in the library and do stuff to them, multiply them by numbers and add numbers to them, certain kinds of transformations. But if we simply go through and plug in -1, we'll get out 3. Though I don't use -1, I'll have to do a little open circle thing again. -1, 3, -1, 3. Actually, it's the same little open circle we had before. Plug in, say 0, we'll get out 1. 1, we get out 3. 2, we get out 9. Leave it to you to check the arithmetic on that. So we get a handful of little points here. 2, 9 actually runs off my scale. That one's somewhere up here. We get this kind of parabola shaped thing. Not a coincidence. It's got a similar shape to the x squared function. It's a bit narrower. X squared itself would open up a little bit more widely, as we'll see next time when we look at transformations. But plotting a few points, we see a general shape that looks like this. My apologies, that's all we can do at this stage. And this is a graph of the function. If you'll believe me on the parabola part, I use 3 or maybe 4 points. I got the imaginary one up here of 2, 2,9, so it's somewhere up here. It continues upwards and passes through that. But we've got a straight line segment for this piece. We've got a single point right there for the middle piece. And we've got this thing here that's shaped a lot like x squared for the rest of it, for the 2x squared plus 1. A single function, 3 pieces, and there's its graph. Well, if we've got the graph, now we can talk about range, and they ask us about extrema as well. Oh, no, they ask about continuity. Hey, what's the extrema? Does it have a lowest point on the graph? Yeah, that one right there. So the minimum of the graph is 0. The output of the function is 0 here. Input's -1. That's where at -1, the graph has a minimum of 0. It's point -1, 0. What's the range? So I look for y values. Get these y values out, get these y values out. Actually, these up here, I get them all out twice, once on the left and once on the right. 5, for example, comes out here and here. 3, well, I only get 3 out once. It's got a hole poked in it on the left, but we do get 3 out. Down to 1, we get all those out. Between 0 and 1, there's nothing drawn. Between y equals 0 and y equals 1, I'm sweeping left and right because I'm looking for y values, points on the curve at this y value. So between 0 and 1, there's nothing there. At 0, there's that point. Below 0, there's nothing drawn. So the range includes 0, the y value here. Then there's a little gap, and it picks up at 1. Includes 1 and everything greater than 1. The range is a set of y values for which there is a corresponding point on the graph of f. So we see from the graph, the range includes everything greater than or equal to 1 up here, along with 0. Y equals 0 itself because of that single point, the y coordinate of which is 0. So the range is 0 union everything greater than or equal to 1. Here it is written in interval notation, combined a little bit with some set notation. Ranges are hard to find unless you have graphs. Well, we're working on graphs. That's why we're talking more about ranges these days. How you feel about continuity? Draw it without picking up my pencil? Yeah, it's a straight line segment there. Oh, we got a little hole in it. I had to pick my pencil up and then pick up down here. Well, I'm sorry, I have to pick my pencil up, go and put that dot down there. Pick my pencil up again, and then trace out the rest of it. It's discontinuous. It's got a hole in it right there. And the value is down here. If the value of this point were there, then we could draw it without picking up our pencil. Might have a little point in it there. So pointed there because it's curvy. The, what was it, 2x squared plus 1 part is generated something curvy, and this is a straight line segment. So I expect a little point to it there. It's not smooth at that point, but it's got a hole at that point, and that addresses the continuity. So not continuous at x equals -1. So there's dealing with a piecewise function and producing a graph. Here they give us a graph and ask us to find the piecewise defined function. Okay, 2 pieces. The information they're giving us, they intend us to take those both as lines or line segments. All right, left piece, the straight line passes through these 2 points. We can find the equation for a line through 2 points. Over here, straight line passing through these 2 points. It wants to pass through that point too. We could use that. We could use 0, 0 as a point on the line to find the equation of the line. we couldn't use that as a point on the function f, right? Two different things. I'm talking about the line. The line, that's defined for all x values, but you only use it in places. But we'll base on the dark points that they've given us. We'll base our computations on those. The left piece is a line segment containing the 2 points, x1, y1 equals -1, 0, that point, x2, y2 equals 0, 2, that point. Well, we're good at finding equations of lines. We'll find a slope, y2 minus y1 divided by x2 minus x1, y2, y1, x2, x1, substituting in and simplifying, doing this a little bit faster. You can always pause it and double check, but we've done a lot of this at this stage. But we get out a slope of 2. Does that look right? It rises 2 and runs 1. Yeah, that's right. So the slope is 2. We'll use the point slope formula. Say we use the point y1, x1, x1, y1 in that formula. So we're using x1 is -1, y1 is 0. Substituting in, that produces y minus 0 equals the slope 2 that we just found, x minus -1. Usual warning, be careful with the parentheses so you don't drop a negative sign. Simplifying, we get y equals 2x plus 2. That's the formula for the function f, provided the x values are between -1 and 0, including the endpoints. -1 and 0, including the endpoints. These are less than or equal to. It's just run off the screen a little at the bottom. These are less than or equals to in both cases. Includes the endpoints. Includes the endpoints because there's solid circles there. So we'll use this piece over that, maybe that range of x values. Let's move to the right-hand piece. New slide. Right-hand piece, same story. We've got 2 points, say 1, 1, and 2, 2. You'll find the slope is 1. You believe that. Rise 1, run 1. Yeah, comes out of the formula, and it's certainly 1. We could then use the point slope form, and one of the points, let's use the 1, 1 point. We get y minus 1 equals the slope 1 that we just found, x minus 1. The minus 1's cancel. You get y equals x. We could have used the point 0, 0 to find the equation of that line. We would have also got y equals x. Oh yeah, 0, 0, 1, 1, 2, 2, 3, 3. I certainly believe that's the line y equals x. I recognize it from the library. So that's the part that we'll use when x values are strictly greater than 0. Right? It picks up right after 0, if that makes any sense. Probably it doesn't. It picks up on the interval 0, comma infinity. For x strictly greater than 0, we'll use this part. So we found the equation of the line that includes this line segment. We've found the equation of the line that includes this ray. We just keep those on the appropriate input values, the appropriate range of x values. So we had 2x plus 2. That's valid for x between -1 and 0, including -1 and 0 because of the solid points, the shaded endpoints. And the other part was x, and that's valid for any x values greater than 0. This is how the book expressed their piecewise-defined functions. So that's how we can take a graph and turn it into a piecewise-defined function. So they've given us functions and had us graph them. That's fine as long as they're in the library of functions. And they've given us graphs and asked us to find the functions. That's okay as long as we can take that graphical information and turn it into equations. We can for lines. And maybe that's about it. Reliably, that's about it. So maybe we could do some things with some square root functions or whatever. We'd have to recognize them from the graph though. Certainly lines, I don't have a problem with. So we've taken graphs and created functions and created graphs. They didn't ask anything else about this, I don't think, but hey, there's a lowest point on the function, only occurs here, right? Not included there. The minimum is y value of 0. Doesn't have a maximum, it's unbounded in this direction. Domain, do we deal with domain? Starts here at -1 and includes everything else, as you can see from the graph, as you can also see from what's spelled out here. It's not continuous, of course. I can draw this piece, pick up my pencil, and then draw the rest of it. So it's not a continuous function. One of the reasons you look at piecewise-defined functions is to get illustrations of functions that aren't continuous. So that's a common use of them. All right, one final question straight out of the book. They've given you way more information than you need. This involves some ugly numbers, so we'll mostly just glance at this one. It says 2014 tax rate schedules are given in the accompanying table. If X equals taxable income and Y equals the tax due, construct a function Y equals f of X for schedule Y sub 1. This is schedule X. This is when you're single and filing your income taxes. They want us to talk about schedule Y1. This is married and filing jointly. So all this stuff in the table is irrelevant to this question. These are the numbers that are relevant. All right, they want us to define as a function of taxable income the amount of tax you owe. Here they talk about taxable income. They say if it's over $0, if you made anything, or then here's the line of information. If it's over 18,150, here's the line of information. If it's over 73,800, here's the line of information, and so forth. Dealing with a piecewise defined function. When the income is between 0 and this, you use this information. When it's between this and that, you use this information, right? There'll be some half open, half closed intervals we'll deal with. Now, we got to take also this income thing and deal with it in terms of a taxable amount. If you made over $0, but not over 18,150, then you're taxed a flat rate of 0 plus 10% of the excess over 0. That would be everything you made. You're paying a 10% rate under those conditions. If you taxable income X is over 18,150, but not over this, so that would mean taxable income is greater than this and less than or equal to that. Then you're going to pay this amount plus 15% of the amount of your income that's over, excess over 18,150. The idea is you reach a percentage that you pay, and then when you move into that next tax bracket, you pay that percentage, plus you pay tax on the amount between the bottom of that tax bracket and the top of that tax bracket. Clear as mud. Actually, we'll make it a piecewise defined function, and the piecewise defined function is a lot easier to use in the chart. Okay, so let X be taxable income. We see that first, if X is between 0 and 18,150, between here and here, strictly greater than this, over $0, but not over this, so less than or equal to this, less than or equal to is what we get out of that. Then the tax is 0 plus 10% of the amount you made, the excess over $0. Well, you made X altogether, so 10% of X, so it will be 0 plus 0.10X. Let's do another one. If you made more than 18,150, but less than or equal to 73,800 taxable income, that puts you between these two numbers, then you're going to pay 1,815 plus 15% of the excess taxable income over 18,150. Notice this number is the lower number in that tax bracket. So how much more than 18,150 did you make? Well, you made X, subtract 18,150 from it, that's the excess. So you've got the flat number of 1,815 plus 15% of however much more than 18,150 you made. Let's do another one while the chart's in front of us. So next we'd say, if X is strictly greater than this number and less than or equal to that number, then you'll pay this much plus 25% of X taxable income, which is at least this big. That's why you're looking at this bracket, minus that. So we'd get this number to replace the previous 1815, right? The 1815 is replaced with that number. The 15% is replaced with 25%. So the 0.15 becomes a 0.25. And the X minus that is replaced with an X minus this. So we'd have not X minus 18,150, but now X minus, what was it? 73,800. That's the pattern. That produces the following in the same way. It's always, if you lie in a certain range, then you pay a flat rate plus a percentage of the amount you made above that lower bound on that tax bracket. There's the amount you made, there's the lower bound subtracted away. This is what they call that excess income. That chart produces these things, so we can use this stuff over here on the right as output of a function. So you get this stuff as the output of the function, and it's a piecewise defined function. X being taxable income determines which piece you use, which bracket you're in, and the brackets affect the numbers. So that's an unelegant example, but once you get this function, this is easy to use. I use software to fill out my taxes, so I don't have to go through charts anymore. But that software is doing this. It simply takes taxable income, finds which piece to use, and computes it based on that. So this is easy to use. That chart's a mess. It contains this exact same information. But if you use software to do your taxes, make a reasonable assumption these days, it's got built into it functions like this. So this allows us to take that icky table and replace it with, and granted there's some icky numbers there, but it just replaces it with this function. You take your income, find where it lies, plug it in there, you're done. You've got your tax due or taxable amount. And that takes care of piecewise defined functions. So we've got a library of functions now, and in that library of functions, we've included some powers of X, reciprocal functions, square roots, cube roots, squaring, cubing, and we've looked at piecewise defined functions. We'll deal a bit with piecewise defined functions in this class, and you'll see them a good bit in Calculus 1 as well. So that's the reason we're covering the piecewise defined stuff in here. So you're good to go. We've got 2 more sections, I think it is, left in this chapter. And in those 2 sections, we'll elaborate on some other things as to how to take the library of functions and graph some things that aren't in the library of functions by making transformations and so forth that popped up in one of those exercises we just did. So there. So have a nice day. I'll see you in the next section here in a little while. We'll continue graphing. Have a nice day.